Okay, this is lecture 21 of our DTCO 2025 lecture, and this lecture is pre-recorded because of my business trip to Incheon. So I will make a short presentation, and please start your own exercise. So in the previous lecture, we made a single fin fat. And after that I tried to simulate that one, so I have shown you the equilibrium solution, but due to the heavy workload of my workstation, so it was not possible for me to perform the drift diffusion simulation result within a reasonable time. So now it is more relaxed, but anyway, it is always good to have efficient simulation. So in this slide, I would like to one way to reduce number of vertex points. So how can we reduce the vertex count? First of all, we generated the entire structure. After that, for given position, so we just etch everything except for this deep substrate very initial region. Then you will have this structure. Then where can you find the source and drain? Yes, here source and drain, and this is a gate. So we are considering just half of our source drain epitaxial region, but I said that's completely okay. So by etching unnecessary parts, so now we have only 100,000 vertex points in this example. Previously we had 160,000 vertex points. This is a huge reduction, so that is quite good to have efficient simulation. But more importantly, we have to select the appropriate name for our solver. My previous NMOS.CMD example file did not specify correct way the matrix solver name, so there was a missing alphabet R, so you must specify matrix solver, not matrix solver. Okay, so anyway, now we can simulate this structure. So I will quickly show you some result and wrap up today's lecture. This is the input curve without any physical model. Of course, drain voltage equal to VDD 0.7 volt. So using the previous input file with a slight modification for or fixing the typo matrix solve, we must use matrix solver, and now we can simulate the FinFET. In this case, gate work function is set to be 4.4 electron volts, and from my own experience, it takes time, so it's about slightly more than 1 hour in my workstation environment, and it may vary in your own exercise workstation. So please start your simulation now. In this case, without any physical model means that I have not considered any mobility model, and I have not considered any recombination model. And in this case, op current is given to 4.1 nanoampere. So this is 0 volt, and gate is 0, and drain is 0.7, and its value is about several nanometer scale. And after that, here we have popping. For one single fin, we have more than 700 microampere. This is really insane value, so we cannot trust it, but it is obtained only because we have simulated this device without any physical model. Another one is here for your eye guide. I have drawn roughly 60 millivolt per decade line, and you can see that the level of our current, subthreshold current in this case is quite close only slightly degraded from this 60 millivolt per decade ideal case, because this is the FinFET multi-gate transistor. And now I wanted to show you just two more slides. One is work function. What is the role of work function? So as we have seen in our previous lectures, so in this semester, our structure does not consider the proper internal structure of gate stack. So gate stack contains many layers for high K, and also we have to introduce the work function metal and tungsten film. However, in our implementation, we have just pure silicon dioxide with a given thickness and tungsten film. So basically, work function cannot be adjusted by that way. So we must use this work function as just a fitting parameter to match our IV curve. So if we introduce a work function of 4.5 EV, so 0.1 EV higher than previous one, then as we expected, this curve just parallel shift toward positive direction. So you can see that there is exactly 0.1 EV volt difference in this curve. So since we have made a parallel shift, so op current is more than 10 times reduced, because this subthreshold slope is quite close to 60 millivolt per decade. So if we have 100 millivolt, then that can introduce more than 1 decade difference in our subthreshold current. But on current is not that much reduced, so because this is nothing related with this exponential behavior. So that is the case without any physical model, and now you can understand we can use this work function as a fitting parameter. Then let's go to the last figure we have in this lecture. When we introduce mobility model and SRH model, how can you do that? Just to reuse our previous example command file, then we can get this dashed red line. Gate work function is 4.4 EV, so as shown here, LED and this LED, they share the same gate work function. Their difference is only the model specification, without any mobility model, SRH model. With default mobility model and SRH model, then we can have a severe reduction of drain current and op current. Previously it was 4.1 nanoampere, and now it is reduced almost more than 6 times, I guess. 7 times, yes, about 7 times reduction is obtained here. But more importantly, it is this mobility model introduced huge reduction in this on current. Previously we had a highly overestimated value of higher than 700 microamp. That is not acceptable in reality, and on current is reduced to more reasonable value of a few microamp ampere per fin. So for one single fin, we can expect this level of current conduction. So now you have homework. We have homework 21st, and of course this the due is next Monday, and this figure shows the IV characteristics assumed in the ASAP7 PDK. There are many different lines here. These branches are for PMOSFET, so we don't care about them right now. And these are for NMOSFETs, and they are differed only by their gate or gate work function. Okay, so by changing gate work function, we can also change threshold voltage. Therefore, if we increase threshold voltage in this direction, then of course the leakage current is significantly reduced. It was 2.4 nanoampere, but now it is approaching to 1 picoampere. So more than 2000 times reduction is obtained by shifting the threshold voltage by amount of 0.21 volt. So that is a huge impact in our transistor performance. At the same time, of course, there is another cost for changing threshold voltage. So this reduced off current comes with also reduced saturation current or on current. So almost half of it, over 40% reduction is obtained in this on current. So maybe you can think that, oh, we have reduced on current more than 2000 times, so about 40 times reduction of on current is much smaller than this 2000. However, please note that we must consider the subthreshold current or up current in logarithmic way, but in this on current case, a few percent difference does matter, so we cannot live with this kind of a huge reduction in general case. I mean that since they have these four different devices have their own uses, applications, so that is justified. However, if you have the same option and if its own current shows variation about more than a percent times difference, then that will be a disaster for designers. So they cannot endure that kind of huge fluctuation. So let me just come back to our current example. In our current example, now we have a value about 0.57 nanometer and 33 microampere for off and on current. Then where can you find it? So in the terms of off current, we are somewhere here. And how about this on current? We are here. So in this simulation, in our simulation, we think that our device itself has a little bit less powerful than the one shown in this AP7 PDK. I think that the possible reason is EOT, electric or equivalent oxide thickness. We have used exactly 1.0 nanometer for EOT, and it can have different numbers, so that can be a possible reason of reduced on current under the similar level of our off current. But anyway, for why do not alter the material parameter, we can just live with this present model. So please, in this homework, please just run your simulation with some different gate work function values. Then you can have different curves, and please make a comparison with your off current and the one shown here, and your own current shown here, and your own current and own current shown here. Then that will give you some feeling about concrete number. So please note that this is just virtual PDK, so no perfect matching with our TKD simulation, and this kind of PDK result will not be pursued. I will just leave with our currently available ticket model, and we'll continue our discussion about DTCO procedure. Okay, thank you for your attention, and let's meet once again next Monday. Thank you and bye.